Okay, great. So welcome to lecture 8 of our course. And finally, we're getting somewhere to something which is going to be usable. And actually, today we're going to be talking about an algorithm which, if you talk about privacy preserving NLP, everybody sort of understands this is going to be this algorithm. So differential private stochastic gradient descent, DPSGD. So this is the meat and potatoes of everything people are running and trying to do. So most of that is basically around this algorithm, which turned out to be very useful, like in practice. Okay. But before we went there, we need to understand many things. So let me just quickly recap what we did. So we understand what is the pure differential privacy, so epsilon 0 differential privacy. We talk about the central and local differential privacy. So central, we have the database and curator, and local is like everybody's privatized and then give away. And there are pros and cons. So the central one gives better accuracies. The local one, you need much more data to learn something out of the data. Okay, but it's more private. And then last week, I guess, we talked about this approximate epsilon delta differential privacy when we said, yeah, with some tiny little probability, the privacy loss can exceed this epsilon, but that's maybe fine in some cases. And we talk about this Gaussian mechanism. And there was a case like the privacy loss random variable behaves nicely in a way, which means it's a Gaussian in a way. And then the tails are infinite, but tiny. So they decay very, very fast. And we talk about, like, briefly mention two things that, I mean, that one is the post-processing. So you cannot undo privacy. This is a great thing. And a little bit of the composition. So if you stack multiple algorithms after each other, they will, the epsilons and deltas will sum up in a way. So this is what we have so far, but now let's talk about something fun finally, and it's going to be supervised machine learning and maybe some neural networks training. So before we go there, I think I should recap a little bit of motivation. Why is it important? Because this is something what we saw already in the first lecture or the second one, that if we have trained models, and what we mean by trained models is their architecture and their weight. So the architecture is maybe known, but their weights are somehow important because this is how we train these models. And they can leak some training data. And this is the example from Nicholas Carline and colleagues, that if you take, for example, GPT-2 model and prompt it with some short strings and check whether the answers, the autocompletion, resemble something, you will actually end up with leaking the samples from the model training data. So basically, it remembers something from the weights of the model remembers something from the training data verbatim. Basically, the text is somehow stored in the weights. So you can from the model and ask for, well, what was the email address of John Doe at something something, if you consider this private. I guess in some cases it's really privacy violation. So the models do remember something of the training data, and it's hard to somehow bypass that. So I mean, it's not trivial. So this is one example we talk about, but there's actually a much more beautiful one, which I really like, and I should have shown that this one. It's from computer vision, so not language, but a vision. And this is a so-called, so what Frederickson and colleagues did is so-called model inversion attack. We don't go into details of this attack, but just to show what is possible. So let's say we have a model or a system for facial recognition. Okay, so we have some facial recognition system, and we have API access to this facial recognition system. And this is only what we have. And also the system gives you some confidence about their predictions. So it's saying like, maybe, I'm really confident 80% that this person is John Doe or not. This is all you have. You have black box access to a model through API and maybe some things. And in this paper, they were able to to exploit this access, this API access and the confidence value. And you only need API access and the name of the person whose face is recognized by it. Okay, so two things. But what you're able to do is basically reconstruct something from the training data. And it actually resembles the actual person from the training data. So this is the same person, and you can, they ask also experts, or mechanical Turkers, and they were able to assign these persons with the real one with high accuracy. So this is what is stored in a network. You can really reconstruct the training data. You can reconstruct an image. So wow, okay, if this is personal data, if this were, I don't know, some medical screenings or whatever, this could be super bad. Okay, so networks or models do remember things. We don't do anything about it. Okay, so I think, again, repeating, privacy is hard, even though you say, well, it's just a model. Privacy is super hard. So now we understand that models do remember something. We should also recap or relearn, depending on your background, how can we train models in the first place. So who remembers SGD, stochastic gradient descent? So who knows stochastic gradient descent? 1, 2, 3. Who's never heard of stochastic gradient descent? Okay, so let me just recap, okay, maybe very quickly. So we start with a loss function, and so this is the standard thing from supervised machine learning. So we say we have a couple of labels. So we have a label training set. So these are some feature vectors, and these are the label vectors. So for example, a feature vector of one-hot encoding or back of words. Sorry, excuse me, back of words feature vector, and then we would have like a label, binary label or multi-class label. And we have a per instance loss, which is given this feature vector and some parameters of the model. So what are parameters? I mean, could be weights of a neural network. So basically weights and biases for each layer. These are the parameters, and we usually use this very fancy symbol, big theta. Okay, so these are some sort of parameters. So given the input and the parameters, so the function computes some output, obviously. So function is, for example, the neural network, or logistic regression, which is a very simple neural network, or I don't know, some other algorithm, but basically a neural network. So it predicts some sort of output, and this is the gold standard output, so gold standard label. And the loss is saying, well, how much I'm actually close to the true prediction. So for example, I don't know, we have a cross entropy loss in the next slide, I guess, or it could be a squared loss. So if this is new to you, then let's have a look in closely, and maybe you can ask later, but I assume like everybody's sort of familiar with the loss function, because what are we doing is we want to minimize this loss in order to train the network. So we have n training examples, so we compute the loss for each example, saying, well, the network has some parameters. I'll give you an example, make a prediction. If you're far off, then the loss is going to be high, because I'm going to penalize you for this misprediction. And I'm using this information later on to update the parameters. But just the loss is saying like how much the network is now off, or the model is off for predicting some data compared to the gold label. Okay, so this is the loss function. Any questions? Okay, great. And what we do typically is that we, in training, let's say neural networks, we try to optimize these parameters by minimizing the loss. So these training examples, these are fixed, right? I mean, this is given. We don't change anything about x and y's, but we change this. We change the theta. These are the parameters. And we want to find such a set of parameters that our loss will be minimal. Yeah, welcome. So we have some VIP seats, or take any place you want. Okay, so this is the goal. We want to find such parameters that the loss is as small as possible. What does it mean? Well, for any input, it will be very close to the actual gold standard data. So we want this to be, if this is 0 or close to 0, then it's awesome, because we find like the best parameter. So we want to find such parameters that this will be minimized. Okay, make sense? Okay, cool. So one typical example, I mean, this is maybe not, this is optional now for our course, but I just copy pasted from the last semester NLP course with deep learning. So the one typical example is a binary logistic loss. So you take your gold standard value which is in 0 or 1, and this is something the network predicts and make this computation. So this is one example of a logistic loss, which it penalizes things that are far away. So if you have a zero gold standard and 1 is the prediction, it's going to be penalized, or excuse me, no, if this is the prediction is far away from 0, it's going to be penalized more than if it's closer. So this is one example of the loss. Okay. Well, I'm showing this one. This is like very typically used. So we have an example of a logistic, of a loss. Another loss could be basically saying just, okay, y minus y ahead. So this is the gold standard. This is the prediction squared. So this is the square, square loss. Also like typical in some situations. Okay, so now we want to minimize the loss. We have an example of loss. And what our function actually is, so if you had a course last year in NLP, or if you haven't had and had a chance to maybe rewatch it on YouTube or read the slides or whatever, any other source, we're talking about computational graphs, which basically means you have a function which you express as a computational graph, where each node is some sort of function, like small function, and you just compose them together. So these nodes are the input, these are the weights, and this is the bias, and this is a linear layer, basically, a linear function where you multiply these as a dot product and add the bias. What is this? Anyone remembers or knows that? This sigma? It's effect activation, and what exactly is it going to be if this is sigma? It's a sigmoid, yeah, exactly. It's a sigmoid. Sigmoid. And do you remember this sigmoid function, just out of curiosity? Minus, let's say, what could that be? T. T is input, okay? Yeah, that's it. That's a sigmoid function, exactly. And it's squeezing everything between 0 and 1 as a probability, sort of. And since this is 0 or 1, and we use maybe like a logistic, cross entropy loss, then everything will work out. So this is an example of a very simple, it's actually a logistic regression or a one-layer neural network. So there is no hidden layers in there. What we are actually trying to do in this minimization thing, so we want to find these parameters. Okay, so this is the function, is our kind of this network or this function, like, which is complicated. So it's a linear, then there's a sigmoid and stuff like that. And we want to minimize this function with respect to these two values. Okay, so W, so the set of parameters of weights and biases. And how can we do that? How can we minimize this function? So we have two very important paradigm here, or not paradigms. One algorithm, and we're this algorithm using one, let's say, a trick or a kind of like computational way of computing a thing. So how can we minimize a function with respect to its parameters? How do you minimize functions? Okay, so let me see. Let me ask. So you have a function which looks like that. That's a bad example, but anyways, okay. So where is the minimum of this function? I would say maybe here. Okay. So how do you find this minimum of this function? So this function is like y is f of x. Okay, it's like single variable, and you want to find the minimum. How do you find this? Okay, differentiation. Okay, cool. Okay. I see where you're heading. Okay, so you can actually take a first derivative of this function. That's what you're saying. You take the first derivative of the function, and if you put it to equation equals to 0, it will find you all the points where you have like 0 derivative, right? So it would be here, and here would be like 0 derivative. And then you would try all of them, maybe. Okay, yeah. This means that you can compute, like, this is like sort of closed for solution. So this is what I remember this from high school, where we did this, like, okay, here's the function, find the minimum, and you do it like paper and pen, things like, okay, yeah, here's the derivative. That's possible, but I don't know if it works easily for like multivariate functions. There is a better way. There is something like something better, like computational. Gradient descent. Okay, so what is it? So let's forget this. What is gradient descent? So it's iterative optimization, exactly. So how do we start the gradient descent? Okay, who hasn't heard of gradient descent? Okay, good. I'm afraid we cannot do this today in detail because it would gradient descent is one lecture basically. But absolutely go to lecture number, I guess, 2 or 3 of this deep learning for NLP course where we really talk about gradient descent, like the full lecture, and just watch it and learn it. I mean, there's no magic behind it, but just to know the derivatives of that and how iteratively you do that. So, we use sort of the derivative of the function, which gives you the slope at each point, and we kind of, if we start here maybe, then this is, the slope will be like that, and we take another step, and after some things, we may end up here or maybe end up here, depending on where you start. So this is the gradient descent, okay? So my suggestion would be just, try to learn from these resources, because we are covering that in the last semester. So stochastic gradient descent is the algorithm. And here I'm going to repeat 2 versions of this stochastic gradient descent. And again, see lecture, I guess, 2 and maybe also 3 of natural language processing with deep learning, 23 edition. Everything is on YouTube. You have all the slides, and there's tons of resources on them online, okay? So we have a function that given some parameters and the input, and these are our training data. So these are the feature vectors, and these are the labels. So this is what you want to predict or learn to predict. And we have this loss function, which could be like the cross entropy loss, square loss. So what we are doing is that okay, this is interesting. Stopping criteria not met. Well, it's iterative, so somehow we should stop. Maybe we will stop when the difference will be small or something like that, or after we just run out of computing power. So after half a year of computing, we say, okay, let's stop. We take so here this is the online version, okay? So the online means that we sample a single training example. So we take just one training example. And for this training example, we compute a loss. So this is like, how off are we for this example, given this current parameters? So if the true label would be, I don't know, it's a positive review, and our function now predicts something not really positive, maybe negative, maybe like if positive were 1 and negative were 0, our function is predicting 0.3, then we're penalized quite a lot. So this is our huge loss. And we want this loss to be as close to possible, excuse me, the error be as small as possible, so the smaller loss. So we compute the loss, and then we compute so-called gradient of the loss with respect to the parameters. Okay, so if you don't know what the gradient is, it's something like derivative in 1 dimension. It gives you like where the direction of the steepest ascent. Like, if you go up, basically this is the derivative. And if you are in multi-dimensional setup, then it's not called derivative, it's called the gradient. But basically, the number of parameters determines the world you live in, sort of. Like if you have 2 parameters, then you can imagine it as basically like a landscape. And then if you are somewhere at any point, so the gradient is telling you what is the steepest ascent at this point. So if you're just let's say in a valley of mountains, so the gradient will tell you, what is the steepest ascent, like where you have to go steepest here. So the direction basically, not like the 3D direction, but the 2D direction. So this is the gradient. And if you follow this direction, you will end up somewhere high. We're not maximizing, we're minimizing. So that's why we're taking the opposite step here. So if you are somewhere, let's say on a hill, you don't want to go up, but you need to go down. So you subtract this gradient vector from your parameters, so which means you take a step down the hill, so to say. Okay, so this is the analogy I'm using for if you have 2 dimensions. Unfortunately, this usually never has 2 dimensions. It's like, how big is GPT-4? Nobody knows. How big is Llama? 70 billion parameters. So welcome to 70 billion dimension world. I cannot imagine anything more than 3 dimensions. So this is 70 billion dimensions, okay? It's huge. It's huge. So you're optimizing in 70 billion dimensional world of parameters. The principle is the same. So this is basically, how you train GPT. This is it. This is the algorithm. There is only one algorithm that everybody's using today. This is stochastic gradient descent. Good. So we take a step, and this tiny little thing, the eta is the learning rate, because you want to control how big the step is going to be. So you're going to be small, big. It's a hyperparameter. You have to choose wisely because you can overshoot and stuff like that. Good. So just to sum up, like this is based on a single training example. So this gives us just a rough estimate of the corpus loss. Because you pick one example and you don't know if what you learn as a gradient is like very representative, or the example is some outlier, or well, this is like a bad estimate. You just make estimate based on one simple data item. So it might result in inaccurate gradients. Okay. Any questions? All right. So how can we fix that? What do you think? I mean, how can we fix this taking single training example? Can we fix it somehow? How would you fix that?
The data can divide in testing.
You can divide train and test, but that's not you have to do this like training, testing, but it doesn't have to do anything with the inaccurate gradient. So how do you make the estimate better? You take only one sample at a time. So what you're gonna do, instead of taking one, you take 10. Yeah, you take more, exactly. So you say, well, not a single training example, but I'm gonna compute the gradient for, let's say, 10 examples, and then make an average. So, okay, now we're getting somewhere. We're making an average over a couple of examples, which gives you better estimate of the true gradient. What would be like the true gradient would be like you take the entire data set, and for each of these points, you compute the gradient and then take the average. But I'm sorry, it won't fit your memory if you have like large data set, right? So what we do typically is so-called mini-batch stochastic gradient descent, which means, again, so when all iterative, but now we don't take we don't take a single sample, we take M examples. M is the design choice. And then for each of those, we again compute the loss and at the gradient, well, we divide 1 over M because we're kind of like averaging for all these examples in the batch. We take a gradient and take the average, which was the kind of estimate. Like average is the estimate of the expectation, okay? And take the step. Okay, so how big is M? Well, it depends. It's a design choice and it's an engineering choice, because remember, everything, if you take a couple of examples, everything has to fit in your on your memory. If you're working on GPUs, you don't have endless memory. You have like, I don't know, 80 gigs maximum maybe for a batch. If you have very many examples, very large networks, you're gonna run into trouble. So the batch sizes could be something 16, 32, 64, depending on the model, depending on the problem. But this is not like thousands or hundreds without any tricks. So as it is, some 32 maybe is a batch size I would start with. And typically you really run out of memory, even like nowadays with huge GPUs. Okay, so mini batch stochastic gradient descent. You take just a bunch of samples from your data set. Okay, any question? Good. So now we have the algorithm. So this is how you train your neural network. You have training data, you have your loss, you have architecture of the network, and then you just iteratively train through SGD. So how? And now so we have the algorithm, we have the training data, we have the parameters as the output, and we know that the network remembers something about the training data, so we want to avoid this. We want to protect privacy. So how are we going to privatize this SGD? So we know differential privacy is adding noise, and noise is good because it has some good properties. If you add noise, Laplace noise or Gaussian noise, it will protect somehow privacy with some epsilons and some deltas. Okay. So what can we protect here? We have multiple options. Just if you think about this algorithm, what can we protect? There's, I guess, at least 2 or maybe 3 options. And some of them are better, some of them are worse, but let's try to think. So so the question is now, where can we add noise? What can we noisify here? Any ideas? Where can we put noise? Yeah. The learning rate. So you would say like the learning rate could be add noise. Okay. That's very interesting. I never heard of that, but that's interesting. It might actually work. I don't know, could work. Actually, it could work somehow, but I don't want to prove this like formally if this is like differential private. But okay, maybe there is something. So you would add noise here. Okay, that's a good take. Any other idea where to add noise? Yeah, sorry. Yeah, input first second. So input. Okay. So you would say here, let's add some noise. Interesting. You were saying? You would say here, add noise. Okay. So let's call these options A, B, C. Any other? The gradient. So plus noise. This is option D. I think we just basically run out of ideas. No. We have one more. Yes. We can add noise here. So this is option number E. Nice. I think now we're kind of run, maybe not really. No, wait a second. Oh, well, there is some noise here in the sampling. Okay. Is this sampling differential private? I have no idea. Maybe we can utilize this later. But let's talk about these things. So what could be, okay, let's start with the, from up, from up to bottom. So if we add noise to the data, what does it mean? Okay, so let's say we have a training table. I mean, ADN, we have table all the time. This is like a, table in is the, the assumption of whatever we talk about in privacy, right? We have table of persons. Okay. So let's say we have, again, Elise, Bob, Charlie, Sander, and all these things, and now they have some features, okay? So these will be values like, this will be feature vector. Sorry for my handwriting, it's really horrible. So some values, so value 1, 0.3, 0.75, and all of them. And this option B, which you proposed, it's a really clever idea. What it means is that we would add some noise here. Some noise. Oops, noise. So we would end up with a table, which, again, we have the same data. Also, we can't forget about the labels. So here we have the label. And we end up something which is similar, but is noisified. Okay, what we are.
That's the type on this one that falls out.
Oh, mein Name ist Müller. I mean, if you want to make a fake name, like it would be Müller. I think this is like a fake call. And sorry for this. I was just curious what's going on here. Okay. And it gave a chance for people to leave, which I can understand. So that's fine. Anyway, that's why I don't make any breaks, because if I make a break, then everybody leaves. I learn it in other contexts. Anyway, what we end up here is, what is this? I mean, because I mean, we would basically add the noise to each row independently. Okay. We've seen this before. What is this? This is basically local differential privacy, right? I mean, you would add noise here to the data, so you would privatize a row, and this is local differential privacy. We can do this, but the cost would be like enormous, because in local differential privacy, you need much more data actually like to overcome this noise and learn something from that as compared to the central data, central DP. So this could work theoretically. Practically, the noise will be so huge that it won't just learn anything later on. Okay, so you're basically destroying the data. Okay, so good idea. Empirically, not really. Let's move on. How about, okay, here, compute the loss and the noise. Okay, that could work. Then the gradient and the noise, I think. So if you compute the loss is a real number, okay? So if you add noise to your loss, you might say, well, actually on this example, I scored not that bad, or I scored much better than I expected. Like, imagine this will be somewhere between 0 and 1, for example, for the cross entropy loss, and the label will be 1. If you add noise here, if the true value would be like 0.01, like very bad prediction, so you basically penalize these parameters to relearn. But if you noisify it and to get 0.6 maybe, then you're saying, well, actually, you don't have to update parameters for this example because it was really good. So I don't think it will actually work. I mean, it theoretically could work, but I don't think, I mean, people are not doing this maybe for a reason. So I don't know. I've never heard that. So we're not going to do that either. Yes. I think you can do this. You can add noise, absolutely. I don't know how this, like the privacy guarantees then would work out, to be honest. So let's move to, so I don't know about this one as well. I have no idea. So it might work, but if you want to go fancy and try to do some like proofs on, there was like you proposed this learning rate. I don't know. I don't know if it gives you any guarantees. Maybe it will. I haven't seen that either. But I'm not saying it's a bad idea. So if you're gonna go really fancy, just try to prove this is differential private and maybe some experiments. But people are using that. What I've seen like people are using is, well, okay, you have the parameters, so add noise to these parameters. Like you learn something, so it's a good estimate of your model. So the weights are actually doing what you're doing, and then add some randomness to that. So maybe, because I mean, there is some randomness in the process because you're sampling something randomly. So maybe, it won't break things. But turn out that actually this is also proposed, but not really the best solution, because imagine you train your model like GPT-4, 70 billion parameters, and then you just basically noisify all the, make noise to all the parameters. I think you pretty much will be in the same situation as in the local DP here. You will basically destroy the utility of that. So this leaves us with this option where we gonna noisify the gradient. And it turns out that, well, the stochastic, there is some randomness in the gradient descent already, because you pick a sample and then you pick a multiple of samples. So there is some, this is not perfect. I mean, remember this mini batch. You randomly sample a subset. Is it a good estimate of the gradient or not? Well, mostly yes, depending, the larger the batch, the better the estimate, but sometimes you're off. So there is already some randomness, but it works empirically. This algorithm works. So the idea is like, yeah, well, if you add a little bit of noise here in this gradient, it won't destroy that much the thing, and maybe it will be working. So this was I guess the intuition why, or empirical evidence basically why this works. So we are adding noise, not here, but to the learning. So basically, we're gonna do something with this gradient. We're gonna be noisifying the gradient. Okay, so this is the main idea behind differential private SGD. Okay, so, but we have a couple of challenges that we need to overcome. And the first one is, okay, unbounded gradient. Okay, well, just to make sure that we are on the same page, like that we are understanding why we can make this algorithm differential private. So from our understanding of DP, well, there's a data set and there's a query. And the query asks for how many people is in the data set, or the average, average age, or something, whatever. Well, if you ask for the gradient, so that if you ask for the gradient, so this is the nabla sign of L given something from the data set and the parameters, this is a query, right? You're asking your data set, oh, what is the gradient for this particular data set? It's a numeric query. If you remove one person from the data set, the query will change. The gradient will be different. Or if you flip it, if you switch the person if you switch the row, it will be a different gradient. But basically, this is where we query the data set. We're asking for what is the gradient. So in principle, this is again like a numerical query. Okay, does it make sense? Like this is where we are asking something from the data, so you can privatize it, because then we have the neighboring data sets. If you remove one person, what will happen? If you flip the person, what will happen? It will have some impact on the gradient. And if you privatize the gradient, then you privatize your data, because you cannot undo this. You can compile multiple of these together, so it will work. So we find a bottleneck in this algorithm, and we say, well, whatever you privatize here, whatever you do afterwards, will be privatized forever. And the query we're privatizing is this gradient query. Okay. But the problem is that the gradient. So what do we need it for? In any query, we had this thing called sensitivity. Remember that? Sensitivity. We had a L1 sensitivity and L2 sensitivity. What was that sensitivity? Anyone remembers what is sensitivity? Say again? Yeah, Manhattan distance is L1, yes, right. But what was the meaning of this sensitivity? So it means that if you, yes?
Maximum amount, changing or deleting one sample can change the query.
Exactly. If you remove one person, so depending what your neighboring data sets are, okay? So we have two versions of neighboring data sets. One is data set with LEs and data set without LEs. And if you do query on one and query on the other, what is the maximum difference you can ever have, like in the output? Or if you have data sets where you replace one person, like one is Elise and one is Bob, what is the difference if you run this on one data set or the other? So this is the maximum difference. And it doesn't depend on the data in there, it depends on the domain, right? Remember we had this example of, what was that? The maximum loan in the bank, which was like 1 million euro. And we said like, yeah, you have to know what is the minimum maximum of your function overall, the global sensitivity. It doesn't have to, it can't depend on the data, because if it depends on the data, you were revealing something about the data already. So it has to be known upfront. Like, what is the sensitivity? Okay, good. So sensitivity. But now we have to think about sensitivity in the gradient. So because we said like the gradient is the query, so we're asking for the gradient. The gradient is just a bunch of numbers. It's a vector of numbers. So how will this bunch of numbers change if we remove or add one person in the data set? We don't know. That's the point. It could be anything. We don't really know. I mean, the gradient could be very small if you're somewhere in the valley already, and just the gradient is kind of almost zero. Could be zero gradient, right? I mean, you can end up with zero gradient, especially in deep networks. Like if you remember something from the recurrent neural networks, this kind of gradient explosion and vanishing gradient problem. Well, you have zero gradient, okay. But if you remember also like exploding gradient, what is exploding gradient? Means like the gradient goes super, super high when it reaches, well, infinity. It basically, overflow whatever precision you have on your computer. So the gradient could be super, super steep if I'm in like 2D space. So, the gradient could be super, super steep, and basically it could be almost infinite, like a wall. Yeah. What does it mean for sensitivity? Like if you can have infinite gradient and zero gradient, what is the sensitivity? Possibly infinity, right? The difference between infinity and zero is something super huge, almost infinity, and zero is almost infinity. How much noise you have to add if you have something like almost infinity sensitivity? it will be completely destroyed. Like, you know, the sensitivity is really crucial for determining how much noise you're adding. Yeah, remember, like we had this Laplace distribution, and we said like, oh, actually, if you have like you know, wider distribution of the Laplace, if you have a large sensitivity, you have to add more noise, like, you know, basically almost uniform, and this would be the case. So that's why we need to do something with the unbounded gradient. Okay, so just to recap, the gradient is a bunch of numbers. It's a vector, but in deep neural networks, it could be anything. Could be minus infinity to plus infinity, basically. It's bad. We don't want this, but theoretically, it's unbounded. So we have to do something about it, right? So, and the trick is very brutal. So this is a bunch of numbers, right? So the gradient is just a vector of real number, real number, real number, real number, and stuff like that. Okay. We're gonna say, okay, well, take the L2 norm of this vector. Okay, if we are, let's do like let's do two-dimensional example. Okay, so we have 2 dimensions. This is W1, this is W2, and here's a gradient is a vector. Vector is a point in the space. Okay, so this is the gradient. Two values, and it could be large. I mean, it could be somewhere like really far away, but no, like it's here. So we're gonna say, okay, yeah, let's have a constant c. So this is some hyperparameter, and we're gonna clip this vector. So this is a vector, and we're gonna say, okay, if you cross this boundary of this clipping, I'm gonna kill this and basically make this vector smaller. So this is a visual representation of this formula, right? But that you have intuition. So we're saying whatever exceeds the Euclidean distance to this circle or ball, we're just gonna clip it and move this value here. So this is going to be our clipped gradient. Does it make sense? So this is a vector. I mean, of course, in 3 dimensions, you're clipping on the ball. In 4 dimensions, you're just clipping a vector by its maximum value. So you say, okay, the value is gonna be, well, this is just a fancy way of representing this, like, you know, numerically, or how would you actually implement it, you know, in PyTorch or in some network. But you're saying, okay, the vector is gonna be, you know, scaled down to that it's maximally, well, if it's smaller than, if the gradient is smaller than c, yeah, so it will be divided by 1, which will remain the same. So if this is smaller, there will be no change. And the maximum of 1 and the norm as to c is how much you scale it down. Okay, so this is how you can like interpret this. I mean, this is how it's written in this equation, but basically means like everything which is, you know, which is outside the perimeter will be basically brutally clipped to this to this radius of clipping. Why the heck does it work? I mean, empirically it works. So this is a way how you, given some hyperparameter clipping constant, which is something you need to decide, like could be 1, could be 5, could be 10. I don't know. I've seen empirically some like between 1 and 10, depending on the architecture of the model, depending on the actual task, depending on everything. But you might see like, well, actually, if I clip the gradient, I'm not changing the direction of this gradient. This is cool. I'm not changing the direction. I'm just changing, you know, how far I'm going to get with this learning rate. So I'm not going like overshooting, but I'm just, you know, maybe slow. That's not bad, actually. That's not bad. But what is it doing is that we have this clip this gradient. So which means this function is now has a sensitivity of, oh, something to do with c and the number of dimensions, but I don't have it right now on top of my head. It should be something like square root of d. I'm guessing. Should be square root of d times c would be the sensitivity, but I'm not 100% sure, but I guess it's like that. I mean, 2 dimensions, I would need to double check, but we we have some sensitivity now, which means, oh, cool, we can use some algorithm which we know for this privatizing this query. We know sensitivity. It's a vector of numbers. Voila. Let's use Laplace, Gaussian, whatever you want to use. Okay. So, any question? Does it make sense now? What we try to do? The gradient is the query we're asking. It's unbounded. So we have multiple ways to how to deal with that. And one very crude and brutal one is just to clip the gradient. But it works empirically because we're not destroying the gradient like the direction, we're just destroying the size of the gradient. But we're having now a bounded function. Okay? So empirically this shall to work. Great. So this is problem number 1, okay? But we solved it. We can apply any algorithm, not any algorithm, some algorithm for numerical queries now. Yeah. The problem is, okay, another problem in DP-SGD or SGD with multiple steps is, remember this thing we had like while stopping criteria not met, do all these crazy things with gradients. Okay, so we repeatedly query the data set and asking, oh, what is my gradient now? Do the step, blah, blah, blah. Oh, what is my gradient now? How many steps can we do? Thousands, 10,000s, depending, because you try to minimize the loss. So you start with the first gradient, take a step, another step, another step. In theory, it could be really like tens of thousands of steps. If you're training, well, if you train for half a year GPT-4, there's thousands of steps to be done. Okay, so here's the problem. Last time we talked about this composition theorem, which means, yeah, we are running the same or various privacy mechanisms on the same data. So we said, okay, at the basic composition, the epsilons and deltas, they add up. So if we have k steps, basically we say, well, the overall budget will be k times epsilon and k times delta. Okay, so if each query is epsilon delta, and the second is epsilon delta and so on, we just sum them up. That's why it's called privacy budget. Makes sense? Yeah, but the problem is, if you have like 10,000 steps, and each step, you need to do like, I don't know, maybe epsilon of 1 or epsilon of 0.5, even like epsilon of 0.1, after 1,000 steps, you end up with overall excessively high overall budget like epsilon of 100 and delta of large. So basically you will learn something, but the privacy will be so weak, you will need so much privacy budget overall that it's almost non-private. So this is bad, right? I mean, just simply adding query with large epsilons will end up with super large epsilon. So what can we do about it? So there is another trick, very neat one, and it's called, so I'm just repeating here, excuse me, again, the basic composition is k times epsilon, k times delta, but there's a very cool formal proof of so-called advanced composition that looks very horrible. Like this is, I don't want you to remember. I don't remember this either. It doesn't matter. Like this, some things. But there's this very brutal formal proof of this. That it's saying that if there's another parameter delta prime, and then the epsilon prime with somehow this very ugly formula, and you end up with something which is different than k times epsilon, k times delta. What does it mean? Well, here, this is somehow epsilon is multiplied not by k, but some square root of k and plus some something smaller here and something small here. So this gives us sort of like quadratic improvement with respect to number of steps k. So if we use the advanced composition, instead of simply like k times epsilon, like adding all them up, we have square root of epsilon of them, which means instead of the difference between square root and linear function, so this would be like rising linearly. What is square root looking like? Something like that, right? I mean, it's for 100 steps, it's gonna make a huge difference, and that's what we need. We're not growing linearly, we're growing sublinearly, like we quadratically, I guess is the word. So this is what we are saving. I mean, of course, we're losing a little bit, we're losing a little bit of the delta, So the delta has to be very small for each step, but we saw it's possible with the Gaussian mechanism, so that's fine. So again, trading off accuracy and privacy, but this is very, very important part why this whole thing works and doesn't break up. Advanced composition, and there's, if you're interested in this proof, feel free. There's a couple of books. It's kind of very technical and maybe not necessary for us to understand in this course, but it's formally proven that this actually gives us this boost. Okay, so so let's sum up. First problem, clipping the gradient, that worked beautifully. So we're we can actually do some privacy on top of that. The repeating thing is now solved by, we actually need more steps, that's fine, but we are not excessively adding up all epsilons and deltas, but we are adding up them, with the number of steps being, sublinear, not linear. So this is good. And trick number 3, why this works, is something also from the theory of differential privacy, so-called subsampling. And I actually guess this subsampling is the most crucial part, but I'm not sure. I've never seen like comparison with all these tricks, and maybe somebody did that. I don't know. But the subsampling should help us to reduce the budget in each step, right? So what do we have now? We have a set of steps. So step one takes epsilon. Step 2 takes another epsilon, and so on. And step 10 takes another epsilon. So the naive sum up would be 10 epsilons. This would be the simple composition. Then we have the advanced composition. Advanced composition. This gives us square root of 10 epsilons. What is square root of 10? Okay, let's make it 16. So 16, which is 4 epsilons. Wow, okay, so this is a huge saving. Awesome. Now we understand why it's so good. And if we had this epsilon each step smaller by factor, I don't know, 2, if we had this epsilon like 0.5, we would end up with actually 2 epsilons. That would be awesome. Okay, so we did this trick with advanced composition. That's awesome. But now let's try to make this smaller for each step. And you're thinking like, how can we do that? I mean, we have this gradient, we have this kind of noisifying the gradient. Can we do something about this better? And subsampling help us. So let's talk about what we mean by subsampling. So let's define. I hate these kind of let's define, but let's define something. Okay, so let's talk about a sampling function that takes a data set D in and produce another data set D out. So for example, we have this table, and it should produce some smaller table. That's why it's so called subsampling. It's going to be smaller. Okay, good. And what we're going to do is for each of these entries, we're going to decide randomly. So randomly, we throw a coin with some parameter beta. So Bernoulli 0 or 1 with the parameter beta. And if we get 1, we say, okay, you go to the output. If we get 0 for this entry, maybe here we get 0, we say, no, okay, no, won't be subsampled. So very easy, like you go one by one and basically randomly draw a number saying like, you stay in the data set, you go out. Okay, so this is subsampling. What is important is, I mean, it makes sense now, but just this is very important that the Bernoulli trial is independent from each other. So you basically decide independently throwing a coin for each item independent of the others. And this is known as Poisson sampling for some correspondence with Poisson distribution. I think the Poisson distribution will be the size of the data set. So just so you know, quick sanity check. So what if beta is 1? What are we going to end up with? Beta is 1. What is going to be the output if the subsampling function has this beta parameter 1? Yeah, it's going to be the same. It's going to be exactly the same. Why? Well, because in each of these steps, for each entry, we're gonna throw a coin or make a trial with Bernoulli 1, and Bernoulli 1 will give you always 1, so it'll be always sampled. And also like the other way around, from beta is 0, what we're gonna end up with? Nothing. Okay, so it's gonna be nothing. Okay, so both of them are, I mean, this is okay, but there's no, I mean, why should we do this? So beta 1 makes no sense, and beta 0 makes no sense because we want a data set somehow. So this should be somehow, between 0 and 1. And basically, so the subsampling never tells you how big the data set should be. That's the point, right? I mean, Poisson sampling isn't saying like, well, I want to sample 10 points from these 100 points. It's saying like, yeah, for each of them, just throw a coin, and then what you end up with, you end up with. And I guess you can have Poisson distribution over the size of the resulting data set. Okay, so this is why it's called Poisson sampling. What is Poisson distribution looking like? Depending on, well, okay, Poisson distribution. What was that? I think it was x to minus x times, what is it? Wow, x to j over j factorial. Can somebody look up Poisson distribution? This is some very nasty function. No, not to j. No, this is wrong. This is wrong. This I'm sorry. I don't remember Poisson distribution. There is some parameter. So Poisson has some parameter beta, and there is something very nasty. There are some factorials in there. So have you found it?
Beta power k to e power beta by
E power beta. It doesn't matter. Okay. Anyway, it's not important. It will give like the size of the probability of the size of the resulting data set, but it's a random variable, so the size is not given. This is really yeah, I should remember Poisson something. I forgot it. Anyway. Okay, so you subsample your data. Okay, this is interesting. So can we use it for some sort of like privacy things? And we can. So we're starting with like, let's have a differential private algorithm, A1. So it's epsilon 1, delta 1 algorithm. So this could be like Laplace, it could be Laplace algorithm, could be Gaussian mechanism, one of those, or randomized response, whatever we had so far, exponential mechanism, one of those. So epsilon 1, delta 1, DP algorithm. And let's propose a new algorithm, A2, that has 2 steps. In the first step, we're just gonna subsample our data set using this Poisson sampling that we just saw. So from a big data set to some smaller data set determined by the parameter B. And then we take this algorithm, and instead of running on the original data set, we're gonna run it on this subsample. So we're gonna run this. So for example, what could that be? Okay, we have the algorithm of what is the average income of my data set? 1,000 people, average income with Laplace mechanism. Nice, epsilon 0 differential private, or epsilon 1 0 differential private. But now I'm saying, okay, well, take this data set, subsample a random sample using this Poisson sampling, and then run your mechanism, like the average. So basically you're saying, I'm actually sampling from the whole population or the data set, some smaller sample, and I'm gonna do the query on the smaller sample. Will it be better estimate? Well, no, it's still an estimate. Well, it's getting worse, the estimate, because I don't have a full information, I have just a subset, but it will give me something, and it will be more privacy, as we just see. But the algorithm was like that. Like, instead of asking the query on the full data set, I'm gonna ask on a subset. And what we're getting here, that this algorithm on the, which we first subsampled and then run this, the same algorithm on the subsample, is gonna give us, it's also differential private. So this is great. And what we're getting here is this second epsilon and second delta. So this looks ugly. We'll have a look into that. But this delta 2 is somehow intuitive. It makes sense because it's saying like the chance that something bad will happen to one entry will be smaller by the chance of sampling. Right? If you're in the data, remember the delta. what it was the delta, like, oh, maybe something will bad, something bad will happen, and I will reveal your entry in full. We had these examples in the approximate DP last lecture. So if you're saying, well, the chance that actually you will be in the database is smaller by beta, then the chances something bad will happen is also smaller by beta. So this is somehow more intuitive than this. I'm gonna show you an example of this. I mean, there's a proof if you're interested in why this works. And actually, if you're gonna through this proof, there's some, again, like nested typos, which will make you kind of, it makes no sense, but then if you find the typos, then it works. Unfortunately, sometimes this is it, like you kind of trust the mechanism, and as usual, people make errors, and also in the papers. But anyway, how that looks. So, okay, the subsampling. So how much can we save on the privacy budget? Okay, so if we have no, okay, this is the first algorithm, like this epsilon 1 delta 1, and then we have this epsilon 2 delta 2 after the subsampling, and this kind of equation. So this is the original, and this is after subsampling. If we have no subsampling, so basically this is beta equals to 1. Of course, if we have epsilon 3, give you epsilon 3. Okay, yeah, sure. There is no benefits, right? But then look at this. So if you have beta of 0.2, which means roughly with probability 20%, each sample would end up in the in the subsample. So I'm not saying the size will be 20% of the data set. That's not true. Because this is Poisson sampling. It might be 20%, might be something else. On average, it will be 20%, but it's a random variable, the size. But with probability 20%, each of these points will end up in there. We are saving, so this is this one, this beta of 0.2. We are saving quite a lot on epsilon, depending on the original epsilon. But now, anyway, look at this. If we use epsilon of 1, then for epsilon of 1 on the original, with subsampling 0.2, we have something much smaller. Oh, okay. Wow. If we sample even with smaller beta, so for example, why not? I mean, we have 1,000 examples, 1,000 people in the database, and we're gonna subsample each of them with probability 10%, right? We should end up somewhere around 100 people, somewhere around, because this is distribution, somewhere around 100 people. Maybe it's enough for just to see, like, okay, what's the average income or whatever. But we will get a lot of privacy advances here. So instead of epsilon 1, we end up with epsilon 0.2, like a huge boost in privacy for this query, right? Because people are actually hiding in these, people are hiding their privacy because they're not selected in the subsample. So this is awesome. And this is great for small epsilons. For larger epsilons, the gain, there is still existing, but not that huge. So for example, instead of 5, you get 3.5. Yeah, okay, good. So there is still some savings, but where it really matters are these like low epsilon regimes, where you really get some boost in this privacy, it's amplified privacy. And actually, to be honest, I believe this is the main thing that actually makes it work. So just let me come back here where we were. So, okay. All these epsilon, bad. Simple adding up, 16 epsilon, bad. Advanced composition, okay, 4 epsilons. And now, instead of each of them, it's not 0.5, but for example, if we had epsilon of 1, and now after this amplification, we would have epsilon of 0.4. So what would it mean? 0.4 times 16. What is 0.4 times 16? 6 something. So we would end up with 6. Why I'm saying this? 4 to, it doesn't make any sense to me now. I'm sorry. Yeah, but not 16, but by something to, okay, I'm confused now. Okay, what was this? 4 times epsilon. Okay, so K was 4. K is still 4, but 4 times 0.4 epsilon, which is 1.6 epsilon. Awesome. So these are the tricks. Instead of 16 epsilon, which is completely bad from the privacy perspective, we're gonna say, okay, well, we'll kind of sacrifice a little bit of deltas here in this advanced composition. We're gonna sacrifice a little bit of precision here in the subsampling because we are not, using the full data set for the query, but just a simple, subset. We're getting much better, epsilons here. These are the tricks. And why this is actually matter? Why can we subsample? Well, can we subsample in these gradients? Of course, yes. Why is it relevant to stochastic gradient descent? Because we already did subsampling in this mini batch. Mini batch, if you remember, is here. Well, sample m examples from the data set and then compute the gradient on these m examples. So we're already subsampling data in stochastic gradient descent or mini batch stochastic gradient descent. So we're gonna utilize this, and instead of subsampling batches, we're gonna just replace this with Poisson sampling. So we're not saying sample m examples, but say something else, like give me something that I end up with a small batch. Bam. We have Poisson sampling giving us the privacy boost, okay? So these are the three tricks that we kind of leading us why this stochastic gradient descent with differential privacy works empirically, and we get some meaningful guarantees. So this is the algorithm in full. Looks horrible, but we know everything already in a way. So let me just rephrase. There is a new thing which is called, okay, well, we will finish soon, no worries. We have something, okay, we have number of steps, so we have to determine how many times we're going to run this, because this will determine how many, how much privacy budget we will spend together, overall. Then, in this paper, who proposed this DPSGD, they introduced something like a lot. So it's something like a batch, but not batch, because batch has a meaning. Batch is like you take your data, shuffle it, and cut it into batches, which are always the same size, 32, 32, 32, 32. Well, we know that we cannot expect like how big the lot is going to be because we're going to use this Poisson sampling, so it will vary. But we want his to be somehow roughly around the batch size, because what we're going to do, again, we're going to iterate number of steps. This is the same as in standard SGT. And then we're going to iterate through the training data, like let's say 1,000 samples, and add this example to the subsample, to this lot, with probability lot size over n. So this is going to be our beta, basically like we had before. And of course, if you have 1,000 examples, and the batch size should be so if this were, for example, 100, and we have 1,000 examples, then we get beta of 0.1, right? So we would sample with 0.1 each sample to the subsample, and this is already giving us the boost, right? I mean, this is what we want. Okay, so we would have a batch size of 100, for example. So this is our subsample data with the Poisson sampling, and then we have this sort of like mini batch, and then for each of them we compute a gradient. Awesome. We're gonna clip the gradient. So this is what we saw before. We're gonna, this is again the clipping by the constant. So everything will be kind of falling under, if it's in the ball, it will stay in the ball, or falling on the surface of the ball, so to say, in 2 or 3 dimensions or billion dimensions. So we're clipping the gradient, and then, okay, here's the trick. So we're adding noise to the gradient. Okay, so now we are actually destroying something. Like here, with the clipping, we're just saying, well, the direction is clear. We just make it shorter sometimes. But now we're saying, well, and add some noise. Okay, so, and what we are using here is, what is this? Well, this is the Gaussian noise. This is some normal, like Gaussian. What is this thing? I mean, this excuse me, multivariate Gaussian noise. So, but what does it mean? It's that this I is identity matrix, which means we're adding noise independently for each dimension. So each dimension of this gradient will have a normal noise with sigma squared c squared. So c squared is a constant for clipping, and sigma squared is something that we need to determine from to ensure the Gaussian mechanism. So this is something we decide, and it will influence the epsilon for each step. I actually don't have a slide on that, but this is like from the last lecture. If you remember, the sigma was something like square root of something, delta, blah, blah, blah. So basically, there's a way how to determine your sigma based on the epsilons or vice versa. So we add some noise, and the rest is just a standard stochastic gradient descent. So we add the noise, then we make an average of this lot and take a step and repeat t times, and we get trained model. But now, each of these steps, this basically is making sure this is making sure that each step is EI delta I differential private after including subsampling, and we can add up with them composition and so on. So we can basically reconstruct the overall budget of epsilon and delta for this algorithm. And this will be differential private. So what it means, every single example in the training data set will be protected by epsilon delta in differential privacy. But it's a very complicated algorithm. I mean, there's 3 basic tricks that make it work. Subsampling, advanced composition, and the clipping is basically to make sure that the gradient is somehow bounded, because if it's unbounded, you have infinity sensitivity and nothing will work, right? That's why the C is here in the Gaussian noise. So this will make it work. Any questions? Okay, so the actual DPSGD is proposed by Martin Abadi and other people who are known from the differential privacy and machine learning community. They propose something much more sophisticated in a way how to get the actual each step, the actual epsilon and delta, and they propose something called the privacy accountant. Where is that? Moment generating function, moments accountant, yeah. And this gets very nasty because then we need to, well, what they compute is the moment generating function of each random variable. Have you ever heard of moment generating functions in probability distributions? Okay, so this is a function of random variable. This is a better way of bounding the tails of the distribution in a way. We're not gonna go into details, but it gives sort of like, the tightest privacy bounds, because you wanna be this as tight as possible. What does it mean? You need to use as little noise as possible, but still being epsilon delta differential private. If you add more noise, you are still kind of fulfilling the inequality. That's fine, but you destroy the duality. And the setup is labeled IID examples. Well, I have a slide on the next lecture. Sorry, I have an example on the next slide for that. So the summary. So DPSGD is basically de facto standard tool for supervised training with differential privacy. Okay, so everybody's using that more or less for multiple things. And I'm gonna talk about the examples, I guess, in the next lecture and after it, where we finally go to like, can you train language models with differential privacy? What does it mean? Can you do supervised learning and things like that? And it's implemented in TensorFlow privacy. There's a framework called Opacus and other libraries. But what makes it tricky? I mean, it looks kind of okay, but the tricky part is the data points must be somehow independent, privacy-wise. Remember, like we have the table, Elise, Bob, and Charlie in the first lecture, second lecture, and we said like, well, there are no secrets that are known to the others. You cannot protect secrets of other people. If you know their secrets, you cannot protect it. And I mean, this is the main assumption of differential privacy. Like all these rows are somehow independent of each other in terms of their secrets or privacy. So if you want to use this for training recognition of cats and dogs, what does it mean? Like each sample in your data set has to be a single person or single dog, and they cannot know anything about the other dogs, so to say. So, or anything about other persons or whatever. And this is sometimes violated, and sometimes people just say like, well, maybe. So this is very important to keep in mind. And the other issue is the actual technical implementation is scalability. Because we have this per example thing like this clipping and norm and things like that. And it's actually very costly because most of the most of the frameworks like PyTorch or TensorFlow, they work in batches, and which batches use parallelization. So you parallelize all the operations on the batch. That's why it's fast. If you have to do it per example, then you're losing this parallelization and everything will become super, super slow and even untrainable. So there are tricks how to implement it better. One framework is, for example, JAX, if you have to do that. Okay, and I guess this is all for today. So if you don't have any question, I stop recording right now.